Hello guys, and welcome back to the PyTorch tutorial series. In the last video we talked about the theory behind logistic regression, and we have seen how logistic regression works in detail. In this video we're going to focus on how to implement logistic regression using PyTorch on Jupyter Notebook. But before we move on, I want to revise some concepts that I mentioned in a previous video that I made about the loss functions, especially related to logistic regression. We have talked about the differences between the cross-entropy loss and the BCE loss. So I'm going to give you a slight overview of the differences between these two loss functions and the function that we implement in the last layer of a logistic regression algorithm. We have to see the difference between a binary classification problem and a multi-class classification problem. In case of a binary classification problem, we have to use a sigmoid layer, and in case of a multi-class classification problem, we have to use a softmax layer. And there is some confusion between what kind of loss that we have to use when substituting these two last layers. So in the case of a cross-entropy loss, which is mostly used for multi-class classification problem, we have to implement a softmax layer. And in the case of a binary classification problem, when implementing the BCE loss, we have to use a sigmoid layer. So I'm gonna show you the differences between these two in order to freshen up your mind and catch up with the concepts that we have previously covered. So let's move over to Jupyter Notebook and show you how to implement it using PyTorch. So in the last video we have discussed in detail about the theory behind the logistic regression model. So let's recap some of the concepts, and we will see the implementation of the logistic regression algorithm. During the implementation we're going to be using the breast cancer dataset in order to solve a binary classification problem. We want to identify whether a tumor is malignant or benign. So we're going to use this example to demonstrate a binary classification problem. During a binary classification problem, we might have a negative class and a positive class. So the negative class is a benign tumor and the positive class is a malignant tumor. So last time we have mentioned that when trying to use a linear regression algorithm in order to solve this problem, we see that the line cannot separate these two data points clearly. So we have to come up with a new function that could give us an anise shape, which is going to be more suitable for this type of problem. So in case of a tumor, if we want to classify whether that tumor is malignant or benign, we can put the tumor size on the x-axis and we can put the classes on the y-axis. So in order to identify whether the tumor is malignant or not, we have to come up with a threshold value of 0.5. And if the tumor size is above 0.5, then we classify it as malignant. And if it is below 0.5, then it could be classified as benign tumor. So the threshold for our classifier is at 0.5. And if the hypothesis function or the prediction from our model is greater than or equal to 0.5, we might predict it as 1 or as malignant, and if it is less than 0.5, we might predict the tumor as benign. So the purpose of this function is just to classify whether the tumor is either benign or malignant. And if we use a linear classification model, if the hypothesis is linear, then we might get values that might be greater than 1 or 0, that might be greater than 1 or less than 0. So we want the hypothesis function to fall between 0 and 1. In order to do that, we replace the hypothesis function by a sigmoid function, which is a nonlinear function. And the sigmoid function is this type of function. So when implementing a sigmoid layer, you can see that when the values from our hypothesis function are going to be passed into an additional nonlinear function, and the g of z will have an S shape, and if the values of z, or the output from our linear layer, is getting close to infinity, then the output from our sigmoid function is going to be closer to 1. In the opposite case, if the value of z is getting closer to negative infinity, then our hypothesis function is going to give us an output that is closer to 0. And whenever the value from our linear layer is equal to 0, then you can assume that this is going to be e to the power of 0. It's going to be 1. So the output from our hypothesis function is going to be 1/2, and it is shown on this plot where the function is passing through 0.5. So we have seen the differences between the sigmoid function and the logit function in the previous video. Next, let's see the interpretation of our hypothesis output. So our hypothesis function is going to be the estimated probability that y equal to 1 on any input x. So for example, if you have a set of features x0 and x1, one is going to show us, one is going to be a bias in this case, and x1 is going to be the first variable, which is going to indicate the tumor size. So our hypothesis function might give us an output of 0.7. This is telling us that the patient has a 70% chance of having a tumor that is malignant. So our hypothesis function can be explained by using a probability function. This conditional probability representation shows us that the probability of y equal to 1 given x and parameter theta is given by this representation. So this is read as the probability that y equal to 1 given x parameterized by theta. So the probability that y equal to 0 given x and y equal to 1 given x must always sum up to 1. And we can express one probability in terms of the other probability. Here we're explaining, we're trying to define y equal to 0 given x by using 1 minus the probability of y equal to 1 given x. So now we have chosen a linear function in order to make the values that are outputted by our model fall between 0 and 1. Suppose that we want to predict y equal to 1 if the hypothesis function is greater than or equal to 0.5. So if that's the case, when z is greater than or equal to 0, g of z will always be greater than or equal to 0.5. And if we want to predict 0, then the hypothesis function must be less than the threshold value. And this is similar to the one that we have covered previously. So the hypothesis function serves as a decision boundary that separates between the two data points. In this case, we want to separate between tumors that are benign and that are malignant. So if we have a training set of X and Y, and each instance is represented by using a bracket as a superscript, and if we have M training examples, and our hypothesis function is going to be the linear representation passed through a sigmoid layer, then how to choose the right parameters theta. In order to find the appropriate parameters for our model, we have to come up with a new cost function. First, let's try to use the cost function from linear regression and see what problem it might cause. So if we try to use a simple mean squared error to solve the problem of logistic regression, we can see that it's going to be the difference between our predicted or the hypothesis minus the label y, and it's going to be squared. If we use this cost function, then that cost function is going to be non-convex, and we're going to have a lot of local minimums, and if we want to converge to the global minimum, we're going to have a lot of problem because our model is going to be stuck in one of these local minimums, and it's not going to be able to escape that local minimum. But if we, because of the non-linearity introduced by our sigmoid layer, our cost function is not going to be smooth. In order to solve this problem, we have to convert this cost function into one that is more convex, so that it's going to be able to converge into that global minimum. So the logistic regression cost function is a negative log likelihood function, and if we use the natural logarithm on top of the sigmoid layer, it's going to be much smoother, and we're going to be able to converge into the global minimum. So this is a piecewise defined function, and if our target variable is equal to 1, then we're going to use the negative log of our hypothesis, and if y is equal to 1, we can consider the case that we're going to use the log z function, and when you add a negative, it's going to be the negative log function, so you're going to make it in this manner. So it's going to have this kind of shape. That's why we're using the negative log of z. And if the value of y is equal to 1 and our hypothesis has to be 1, so in this graph we can see that if our y is equal to 1, then our hypothesis is guaranteed to be 1 if we use this cost function. But if our hypothesis is getting closer to 0, then our cost function is going to be infinity. And this captures the intuition that if our hypothesis is equal to 0, then the prediction from our model is getting much closer to 0. But in this case, we want it to be 1. So if the ground truth is equal to 1 and the prediction from our model is going towards 0, we want to make our cost infinity because we want to penalize the algorithm by very large cost. So this negative log of the hypothesis function is the appropriate function in order to represent the case y equal to 1. In the second case, we have the negative log of 1 minus the hypothesis function if y equal to 0. if y equal to 0, we can represent the minus log of 1 minus z, and its shape will be this function. As you can see from the plot, when y is equal to 0, our hypothesis function is predicting as 0, so it's okay. But if our hypothesis function is getting closer to 1, we want to make the cost approach infinity so that we could penalize our model and give us values that is much closer to 0. So by combining these two components of the piecewise defined function, we can combine them into one cost function, which considers both cases. So the cost function can be given as minus y log of our hypothesis minus 1 minus y log of 1 minus z hypothesis. So if y is equal to 1, then this term will be 0 because 1 minus 1 will be 0. Then we are only left with the first case, and if y is equal to 0, then the first term will be removed and we will be left with the second part of the equation. So we have come up with a new loss function that is going to be suitable for our particular problem. But our target is to find the correct set of parameters for our model. And in order to do that, once we identify the correct cost function, we have to implement the gradient descent algorithm in order to find those parameters. So the gradient descent algorithm is just a simple algorithm, and we update the parameter every time by subtracting the learning rate multiplied by the derivative of the cost function divided by the partial derivative of each parameter theta j with respect to each parameter. And we have seen during the backpropagation procedure, we have seen how to compute this value in the previous video by using the chain rule. Here we can notice that once we have computed the derivative, we're going to get this value, and the algorithm looks identical to the linear regression algorithm, but the only difference is now this hypothesis function is going to be the sigmoid one, but during the implementation of the linear regression algorithm, this hypothesis function was just theta transpose x, and that's the only difference between the two when implementing the gradient descent algorithm. Now that we have covered all of the concepts that we mentioned in the previous video about the theory of logistic regression, we have to recap the differences between the sigmoid and softmax functions and the binary cross entropy and cross entropy loss functions. First, the sigmoid function is given as 1 divided by 1 plus e to the power of minus x, and the plot is shown below, and it's typically used as a last layer for a binary classification problem. And if we want to solve a multi-class problem, then we have to use a softmax function instead of the sigmoid function. For example, if you have scores or logits from a linear layer given as 2, 1, and 0.1, first, for a multi-class problem, we need to convert them into probabilities, and the sigmoid function cannot convert these values into probabilities because now instead of 2 classes we have more than 2 classes. So the softmax function, by using this formula, which is e to the power of yi divided by the summation of each prediction. So we're going to take the exponential of all of these y pred values, and then we're going to sum them up on the denominator, and this function is going to enforce the rule that the sum of all of these probability values is going to be equal to 1. And it's good as a last layer in multi-class classification problems. Now that we have sorted out the difference between sigmoid and softmax function, we have to see the difference between the cross entropy and binary cross entropy loss. The cross entropy loss is mostly similar to the negative log likelihood loss, and we can use in one-hot encoded class labels. And one-hot encoded class labels is just converting the class labels into ones and zeros. For example, if the classes that we want to predict are 0, 1, and 2, the first class can be represented by turning the first index as 1 and turning the rest as zeros. If we want to predict the second class, then we have to make the first one 0 and turn the second index to 1. So that's just a one-hot encoded class label. And the probabilities that we get from the last layer, softmax, are given as below, and we can see that all of them will sum up to 1. And by using this loss function, the cross entropy loss, we can get the final loss value. And this is another case, and we got a loss of 2.3. So in order to implement the cross entropy loss, we can use the neural network package. So one thing that we need to pay attention to when implementing the cross entropy loss is that the cross entropy loss under the hood applies the log softmax and the negative log likelihood loss. So when implementing your model, you don't need to implement the softmax layer by yourself, because the cross entropy loss is already taking care of that by using the log softmax function under the neural network package. And you have to use the class labels that are given originally and not convert them into one-hot encoded vectors, as might be the case when you are working with keras. Mostly when working with keras, we convert them into one-hot encoded vectors. But on PyTorch, we just have to use the class labels as they are. And the predictions has row scores or logits, and we don't need to implement softmax by ourselves. So these are two things that we need to pay attention to when trying to implement the cross entropy loss. So let's see the two cases of sigmoid and softmax using a problem. If we want to classify whether a dog is in a picture or a cat and dog classification problem, then we can pass the image through a bunch of linear layers, and finally when we reach the last layer, we have to implement the sigmoid so that we could convert the logit scores into probability values. Here you can see that it's giving us, it's 90% confident that the image is showing us a dog, so the answer might be yes. So in PyTorch, we have to use the binary cross entropy loss if we want to implement a binary classification problem. And you need to make sure that you add the sigmoid layer at the end, because binary cross entropy loss does not implement the sigmoid layer under the hood, which might be the case for cross entropy loss. So the difference between the BCE loss and the cross entropy loss is, the first one is that the BCE loss is used for binary classification problem, and the cross entropy loss is used for multi-class problems. And the cross entropy loss implements the softmax layer by itself, and the BCE loss does not implement the sigmoid layer by itself, so you have to take care of the sigmoid layer by yourself. Finally, when trying to implement a softmax layer for a multi-class problem, for example, we might assume that we want to classify more animals. We can see that the cross-entropy loss can be used, but we don't need to implement the softmax layer at the end by ourselves, because the function itself implements it under the hood. Now we have finished talking about the theory, and we can start the implementation process. So first, before demonstrating these functions using PyTorch, let's see how to implement softmax using NumPy first. So we need to import the torch package, the neural network module, and since we're using NumPy, we have to import NumPy again. Here we have already seen an example where we convert the logit values into probabilities using the softmax function. So as you can see in this image, we're trying to implement this, and these logit values is going to be an array, and we're trying to convert them into probabilities by defining a custom function softmax using NumPy. So we're defining a custom function softmax, and we can write the equation as np dot the exponential function of x divided by the sum of np the exponential function of x, and x is just a NumPy array which consists of the logit values. Then we're going to pass this logit scores inside our custom-made softmax function, and we're going to see the output from our custom-defined function. As you can see, these are probability scores, and you can add them in order to make sure that these values add up to 1. We can also replace the implementation using NumPy, which we did here by using a custom defined function, and replace it with the 1 by using the softmax function from the torch module. PyTorch provides us with a softmax function that pretty much does the same thing as the function we have defined before. We're going to pass the same tensor x into the softmax function, and you need to pay attention that we are using a NumPy array here, and we're converting the list into a tensor. You cannot use a NumPy array inside of the softmax function. You need to convert it into a tensor. Here it's giving us the same result, but here we're getting a tensor as an output, and here we're getting a list as an output, and all of them will sum up to 1. Now that we have seen how to implement the softmax function using NumPy and PyTorch, let's see how to implement the cross-entropy loss using NumPy first, and we will see how to implement it using PyTorch. First, we're going to define a custom function known as cross-entropy, which takes the actual and predicted values as parameters. We're going to get a EPS which is going to make sure that our predicted output from our model is going to fall between EPS and 1 minus EPS. This is just a very small value, close to 0, and np.clip will make sure that the predicted value falls between the range of EPS and 1 minus EPS. So that's what these two lines of code are doing. And next we have to implement the negative log likelihood, which is the same as the cross entropy loss function, and it's given as negative of the actual value multiplied by the log of the predicted value, and we're going to sum them by using np.sum. And don't forget to put the negative, because it's a negative log likelihood function. Once we have computed the loss, we can return the loss from the function. As an example, we're going to define 3 classes, and each of them are one hot encoded representations. So in the case of class 0, we're going to turn the first index to 1 and the rest will be kept as zeros. For the second case, we're going to turn the second 0 into a 1, and it's similar to the last class 2. Here the actual class is going to be 0, so we want to predict the first class, and we can consider 2 predictions from our model. The first prediction might be good and the other prediction might be bad, so we're using 2 NumPy arrays which consist of probability scores, and these probability scores will add up to 1. Since the first one is giving us a probability of 0.7, it's telling us that it has a higher confidence for the first class, so the prediction is good. But for the second case, it's saying that it's confident that it's the second class, so it's a bad prediction. So in order to see the loss difference between these 2 cases, we can use our custom defined cross entropy function and pass the actual value y as the first argument and the 2 predictions as a second argument. Then we can see the difference between the 2 losses. Here you can see that the first loss using NumPy is 0.35. It's a very low loss, which makes the prediction good. And for the second one, since the prediction is very bad, it's giving us a higher loss, which is closer to 2. Second, we're going to implement the cross entropy loss function, but instead of using NumPy, we're going to use the cross entropy loss function from PyTorch. Here we have already mentioned that we cannot use one-hot encoded vectors in order to represent the actual target variables. So the first thing that we need to do is to create a tensor in order to represent the first class, and this is the tensor that says the actual target variable is the first class 0 and it's not one-hot encoded. Here we have a different set of predictions, and one thing that you can see here is that we are using unnormalized and scores, and these are not probability scores. If you add them together, they're not going to add up to 1. The reason that we are doing this is because we have already mentioned that the cross entropy loss function from PyTorch implements the softmax layer under the hood, so we need to pass logits or prediction scores which are not normalized. So we're going to use the loss that we have defined here, and we're going to pass the predictions as the first argument and the target variable as the second argument to this loss function. So the cross entropy loss is going to convert these 2 logit scores into probability scores by using the softmax layer first, and it's going to compute the negative log likelihood loss under the hood, so we don't need to worry about the implementation by ourselves. Once we get the loss by using the prediction and target variables, we're going to output them so that we could see the difference between the two. We can see that for the first case we're getting a loss of 0.41, and for the second case we're getting a loss of 1.84. This is saying that the first one is a good prediction and the second one is a bad prediction. So the actual class is 0, and the prediction from the first is telling us that it's 0, which is similar to the actual class. And the second prediction is telling us that it's 1, so it's a bad prediction. And we're getting these values by using the torch.max function and trying to see which one is the maximum between the good prediction and 1 and the bad prediction and 1. So this is an example where the number of samples is equal to 1. We only have one sample and we're trying to predict this sample. What if we have a greater number of samples, or for the case n samples greater than 1? So this particular example is telling us that we have 3 samples, and for the first sample the actual target is 2 and the second one is 0, and for the last one it's 1. For this case we need a tensor which has a shape of n batch by n classes. N batch is telling us the number of samples by the number of classes. So the number of rows indicate the number of samples that we have, and the number of columns indicate the number of classes. So the first row is predicting a class of 2, which is similar to the target, and the second class is predicting a 0 because it's giving us a higher value for the first element. So it's similar to the actual label, and the last one is giving us higher confidence for the class 1. So this is a good prediction overall, and the second one is a very bad prediction. And we're going to we're doing this by ourselves, but we can use the loss function and see the difference between these two predictions. So by using the loss that we have created in the previous example, we're going to compute the loss between the prediction and the target variable. Once we have computed the loss, we can output it here. Here it's telling us that the loss for the first one is very low, which is around 0.28, and for the second one it's giving us a higher loss. And you can see the prediction from our first tensor is actually very good, and it's similar to the actual label. But for the second one, it has missed all of them. It's giving us 0 to 0, which is not similar to 2, 0 and 1. Now let's see how to implement a full binary classification model. So in the previous video that I made about linear regression, we have seen a simple way of how to create a model by extending from the module class of the neural network package. Whenever you're defining a model, the first thing that you have to do is you have to initialize each layer of the model by using the init function. And here we need to pass the input size and the hidden size. Input means the input size of for the first linear function, and the hidden size is the output from the linear function. So for the case of a binary classification problem, when creating the model, the second function that we need to define is the forward method. Here we're going to pass the input variable x, which is going to be our set of features, and we're using the linear function from the neural network module, and we're defining the input and output size and assigning it to the variable self.linear1. This is an object-oriented programming approach for creating an instance of a model for PyTorch. The second one, we're creating an activation function known as ReLU. And the third one, we're creating another linear layer, and the input size is going to be equal to the output from the first linear layer, and the output is equal to 1, because in the case of a binary classification problem, the output is always going to be 1. In the forward method, first we're going to pass x in the first linear 1 function, and we're going to get the output, and we're going to pass these output into the ReLU function and get the output from the ReLU function and pass it to the second linear function. Once we're done, there is a nonlinearity introduced by the ReLU function, but this linear function is not going to guarantee us that the output from our model is going to be a probability score. So we need to add a sigmoid layer and apply it on the output from the previous layer in order to get the prediction from our model and return it from the forward function. So in order to instantiate our model, we're going to use the name NeuralNet1, and we're going to pass an input size of 28 by 28 and a hidden size of 5, which is going to be the hidden layer. And the criterion, if you want to use a binary cross entropy loss, then you have to call the BCE loss from the neural network package. If you want to implement a multi-classification model, then you have to you can pretty much use the same thing as before, but the only thing that we are going to add is the number of classes, and this number of classes is going to be the output from our model, and we're going to replace the 1 here by number of classes. The rest is going to be the same, but if you want to use the cross entropy loss, remember that we don't need to implement softmax by ourselves. So we're not going to use either sigmoid or softmax here. You can just leave it as it is, and once you have instantiated the class, then you can use the cross entropy loss and it will take care of the softmax function by itself. Now let's see, now that we have seen the difference between these two, let's implement a full model for logistic regression using a dataset from scikit-learn. So first we're going to import Torch and the neural network package, and we also need NumPy for the normalization procedure. Just as we did in the linear regression video, we're going to import the datasets module from scikit-learn, and in the case of linear regression we didn't need to normalize the dataset, but in case of logistic regression it is mandatory to pre-process the dataset before we fit it to our model, so we have to use standard scalar from a scalar dot preprocessing. There are different methods of normalization, but for this particular example we're going to implement the standard scalar. You can also use the min-max scalar, which uses the min-max function in order to normalize the dataset. Second, we need to import the train test split from a scalar.model selection. We're going to use this to split our dataset into training and testing examples. Finally, we need a matplotlib for plotting purposes. The first thing that we have to do is to prepare our classification dataset, and by using the datasets module, we can call load the breast cancer dataset, and this dataset has data and target, and once we assign it to the variable bc, we can call them using .data and .target, and we can see the shape of our data and the target variable by calling x.shape and y.shape. We can see that our set of features has a shape of 569 by 30. This is telling us that we have 569 different instances, and the number of feature for each instance is 30, and these are the number of attributes. The target is showing us that we have 569 targets for all of the examples. In order to see the first instance, we can use indexing and call the first set of feature the first instance and the first prediction, the first target variable. So this is going to be our first instance. As you can see, it has 30 different values, which are the number of features. This is similar to the NumPy arrays that we have created before, but in this case we have more attributes in order to describe more features, and it's telling us that the value for this particular example, the target is 0, so the class belongs to 0 or benign tumor. So here we can get the number of samples and the number of features by using x.shape, so we are separating these two values because we need them later on in order to reshape our tensor so that it could be n samples by n features. Next, we're going to split our dataset into training and testing sets by using the train test split function. First, we're going to pass x, and second, we're going to pass the target variable, and the test size is going to be equal to 0.2, which is going to make sure that we're going to use 20% of our dataset as a testing sample. Then we're going to output the shape of the training and test sets. Here we can see that we are using 455 instances as training for training purpose, and we're going to use 114 samples for the test case. Next, we need to normalize our training data, and we need to fit the test data using the pre-computed mean and standard deviation. So in order to normalize our dataset, we're going to use the standard scalar class, and by using and we will assign it to the variable sc, and we can call the method fitTransform in order to compute the mean and standard deviation using the entire training dataset, and normalize it by using that mean and standard deviation. But in the case of the test dataset, we're going to use the transform function instead of the fit transform. This is not going to compute a new mean and standard deviation, but instead it's going to use the mean and standard deviation that is computed using the training dataset in order to normalize the test dataset. So here, the only purpose of using the transform function instead of the fit transform is that we don't need to compute a new mean and standard deviation using the test dataset. After normalization, first let's see the first instance of our training set, and let's see the maximum and minimum values. Here the maximum value is 3432 and the minimum value is 0, so it's not normalized. So after normalization we can see that by using the standard scaler, the values are getting much closer to each other. Most of them are ranging from -1 to 1, but we still have a maximum value of 11. After converting the NumPy array to next we need to convert the NumPy array into a tensor so that we could use it inside of our PyTorch model. So we're going to convert both the training and test sets, both the feature and the target variable, into a tensor by using the from NumPy function. Then we're going to reshape the target variable from the shape of 455 to 455 by 1. We have already done this by using the view function. We can also use the reshape function from Torch to do the same thing. So the first number is just the shape of the target variable, which was 455, and we're going to add an extra dimension of 1 so that it has the appropriate dimension for our PyTorch model. Since it is a binary classification problem, we're going to implement a logistic regression model, and here it only has a single linear layer, and the input-R model is going to have n input features, and the output is going to be 1. And in the forward function we're going to apply the self.linear that we have created here on X, and we're going to pass it on to the sigmoid layer to get the prediction from our model. So this is a simple binary classification model, and here we need to pass n features as the number of input features. Notice that we have retrieved these values from x.shape here. Finally, we need to instantiate our loss and optimizers. So we're going to use a learning rate of 0.01. We're going to use the BCE loss as our loss function, and we're going to use stochastic gradient descent as our optimizer. Here, once we have created the model, we need to get the parameters and pass it into our optimizer as a first argument, and we need to pass the learning rate as a second argument. Then we can start our training loop, and we're going to train it for 100 epochs. First we're going to pass xtrain into our model and get the prediction values. Then we're going to compute the loss by using the predicted output and the training values. ytrain is the target variable, and we're going to use loss.backward in order to perform the back propagation. Then we're going to use optimizer.step Then finally we need to zero out the gradient before the next epoch. And let's see the training. And here we have we didn't run all of these lines, so let's run them first. Okay, there was a conflict between the model that we have created before and the new models that we have created here because they have the same name. So make sure you run this line before you start the training loop. Here you can see that our loss is decreasing and it's going down to 0.25. Once we have completed the training loop, then we can evaluate our model. Notice that whenever you start the evaluation procedure, you have to use the torch.nograd method in order to make sure that this is not part of your computational graph. So here we're going to pass the test set into our model and get the predictions from our model. Then we can see the results, the first prediction before rounding, and we can see it after rounding. Here we're performing the rounding because the output that we are getting from our model are going to be probability scores because we're using a sigmoid layer, and if they are above the threshold value of 0.5, the round function is going to round it to either 1 or 0. So if it is greater than 0.5, it's going to be 1, and if it's less than 0.5, it's going to be 0. So after rounding, we're gonna get the ypred class, so it's going to tell us the prediction class. Then we can compute the accuracy by comparing the prediction from our model with the target variable y_test, and we can use the equal function. And whenever we find values that are equal, we're going to sum them together, and we're going to divide it by the shape of the test set. So here we can print the accuracy from our model. Here you can see that the first prediction from our model is 0.68, and after rounding it's going to be 1 because it's greater than the threshold value of 0.5, and the accuracy from our model is actually 92%, and this can be improved by either changing the learning rate or using a more complicated model. So this is basically how you build a logistic regression model using PyTorch, and these are all the steps, and you can combine them into a single Python file. And I broke down each step so that you could understand what is happening on each line, and you can run this code again, and it's going to start another training procedure, and it's going to compute new losses, and in this case the accuracy is going to be 90%. That's all for this video, and in the previous two videos we have seen the theory behind logistic regression model, and in this video we have seen how to implement it in detail using NumPy and PyTorch. If you like my content, make sure you like, subscribe, and share the video, and thank you for watching.
Audio Jungle.